Black holes are not giant sucking machines.
Right.
They just have a gravitational field.
Gotcha.
If you get really, really close, kiss your ass goodbye.
Right.
If you're not, you'll just maintain an orbit around it.
Like we do the sun.
Like we do the sun. Exactly as we do the sun.
Right. We don't crash into the sun. We're not getting sucked into the sun.
Right. And so if you step back, it looks like all the planets are spiraling around, which they are.
Right.
But they're not getting sucked into the sun. Right. All right. So the toilet bowl effect.
Mm-hmm. That's swirl.
These are called spiral arms, and our understanding of them came of age while I was in graduate school. Because how do you maintain that? And because the inner parts of the galaxy actually will complete an orbit faster than the outer parts. So you get this stretching of these coherent cloud formations that, because the galaxy rotates, as we say, differentially, which means the inner parts rotate faster than the outer parts, it will drag it into this spiral shape.
Right.
And one of our big challenges was, how does it maintain the grand design two-arm spiral without over time just winding up on itself?
Right.
Okay, so that's where it got complicated, and we had to worry about what's called spiral density waves. It's not really a physical gaseous structure. The gas is everywhere. There's a density wave that's moving across the clouds, triggering star formation.
Wow.
So wherever this density wave is, there's star formation in that shape. So it's more complicated than it looks, but all I'm saying is everything is just simply orbiting the center of the galaxy.
Right.
And it's not like a toilet bowl that's ultimately going to go down the tube.
Right.
I heard when I was a kid, I said, if you dug a hole from the United States, because that's where I live, where would you come out on the other side? And everyone says, if you dig a hole all the way to China.
Right. That's always the case.
That's how we say
dig a hole to China
here in the United States.
That's right.
However, China is not where you will land if you dig a hole through the center of the Earth. Because if you dig a hole through the center and you start in the northern hemisphere, you have to end up in the
southern hemisphere.
In the southern hemisphere.
Right.
If you start in the western hemisphere, you got to end up in the
eastern hemisphere.
That's how the geometry works.
Is that because it's a ball?
It's a ball.
Right.
All right. So when I did that, if you dug that hole from the United States, you would end up in the Indian Ocean.
Nice.
Okay.
So basically,
the South Indian Ocean.
You just flood the United States.
Yeah,
that's really what you did.
How much do you weigh in water?
I don't know.
Zero.
Nothing.
You're neutrally buoyant. So in water, we don't weigh anything. Put a scale in water and stand on it and read it. Okay? That's what I'm saying.
Okay.
So when you don't weigh anything, then structurally, you're not putting yourself at risk. And that's why the largest creature there ever was is a mammal, and it lives in the ocean.
Right.
It's a whale.
Right.
The blue whale. So when they say, how much does a whale weigh?
Right.
The answer is zero. They give you a weight, and how do they give you a weight? They take it out of the water,
right,
put it on a scale on dry land.
Right.
And then it weighs, gazillion tons, but that's not the weight that the whale feels as it moves through the ocean. The next thing I say may be mind-blowing to you.
Okay.
Okay? The tide doesn't actually come in and out. What happens is there is a bulge of water, two of them on opposite sides of the Earth, caused by the sun and the moon, and Earth turns inside that bulge.
Mm-hmm.
So when we say the water rises and falls tidally, what's happening is we are rotating into the bulge and then out of the bulge.
So the bulge is already there.
It's already there.
And all we kind of do is pass through the bulge.
Pass through, and the water gets high and it gets low. Time for area codes. All right. Well, they already had a set of digits that were reserved for certain tasks. So 411, if you typed 411, that was reserved for information.
Mm-hmm.
You dial 411 and you'd get a human telephone book, basically.
Right.
What is the number of Johnny Jones, whatever, or Mary Smith at this address? They'd look it up, and sometimes they'll dial it for you, or they would just tell it to you and you'd write it down.
Wow.
Right. Okay. Yeah, this is like forever ago. All right. So 611 would be if there was something wrong with your phone and you needed repairs.
Okay.
Okay. So they said, we'll be by tomorrow to look at the phone line, whatever. All right. So they had a few of these that all had a one in the middle. Okay. However, those were established after area codes were established. Okay. Now, they knew we're not going to have a phone number beginning with a 1, nor a phone number beginning with a 0. So the highest population city, New York, they wanted that to be where the area code can be dialed the quickest, because the most number of people would be dialing it.
That's right.
And you don't want to burden so many people with waiting around for the dial to finish dialing.
That's right, because you're going with the finger thing. So
With the finger thing.
Can't have 211, so you got to have 212.
212 is the shortest time dialed area code on a dial.
Yo, that's cool.
Okay, so now, what city has the next highest population?
Probably Los Angeles.
Los Angeles. What is the area code of Los Angeles?
315.
213.
213.
Low. That's why you have this. Okay. What's the next most populous city?
Probably Chicago.
Chicago. What's the area code of Chicago?
I don't know it, but I'm sure it's 214.
No.
Oh.
I can go lower than that. 312.
Oh, 312. That's right. Because you're staying in the little,
You're staying in
the thing.
One was able to stop time. Is it true that you wouldn't be able to see anything because the photons would freeze too? Can we make an exception to that?
You know, I don't know if I have a good answer for that. No. Because to the photon, there is no time. You might have heard that the faster you go, the slower time ticks. This is relativity. And in the limit, at the speed of light, time stops.
Yeah.
Photons, which exist at the speed of light, when they are emitted at wherever they came from, my PhD thesis was on the center of the galaxy, which is 30,000 light years away. And when I captured those photons, for me watching them, they took 30,000 years. But if you're the photon, the instant you left the center of the galaxy, you hit my detector.
You're right there.
In the same instant.
Yeah.
So if there's zero time, I don't know what effect that would have on the photons.
Right.
Because they don't ever have time.
Yeah, they're outside of time.
In a way, they're outside of time.
That the magnetic field was actually reversed at one time.
Yeah.
In the Earth's history.
Oh, yeah.
Woo,
Oh,
that's exciting.
So I don't want to blow your mind.
Okay, hit me.
Okay, really?
I love this.
I say everyone's mind should be blown at least once a day. That's a quote of mine. Yes. I'm just saying. Okay, you ready?
Hit me.
Okay. When we were growing up, the North Magnetic Pole was in northern Canada. It was never where Santa is.
Whoa.
Okay, so Earth's magnetic pole is shifted from our rotation poles. I don't know if you didn't know that?
I did not know this.
And it's not stationary. It moves.
It's moving.
Wait, hang on. So when we were growing up, it was kind of meandering in the Canadian, that whole northern area of Canada where there's just islands and lakes and things. That's where it was, which meant if you were up in Canada, you couldn't use a compass to find north because it could be south of you.
That's right.
Okay, so it's no good way farther down. And you get a kind of right. Good Boy Scout books would have a correction table depending on where you were in longitude.
Incredible.
Relative good Boy Scout books. Now watch, you check it lately. That North Pole has been moving, and it is now passing the North Pole on its way to Siberia.
What?
On top of all that, the magnetic field is getting weaker. And we think it's going to get weaker and weaker until it goes away, and then when it comes back again, it'll be in reverse because it flips every time. We worry that when the magnetic field goes away to flip again, but this is called a dynamo effect, when it goes away and flips, that while it's not there, will it put all of us at risk?
Yeah.
So we go back in the fossil record because it's flipped before. And if you go to the points where it has flipped, there's no periods of mass extinction. So if it wreaked havoc, it was not global catastrophe.
Right.
So I'm not so worried about it. Here on Earth, we have a magnetic field. Not very strong, but we have one. And when dangerous charged particles come from the sun, we call it the solar wind, they see Earth's magnetic field and then they channel themselves away and funnel in at the poles. And they collide with our atmosphere and render it aglow, causing the aurora. So when we see the aurora, that's the atmosphere and our magnetic field shielding us from harmful radiation.